Hello everyone, I'm Subhasree Patro and I'll be speaking about a framework of quantum strong exponential time hypothesis. It's a joint work with Professor Harry Buhrman and Dr. Florian Speelman. Let's begin. Now let's consider the satisfiability problem. Now what is a satisfiability problem? Given a Boolean formula on n input variables, we would like to know if there's an assignment to these n variables that satisfies the formula. Let's look at an example. This is a Boolean formula with three input variables. And the question is there an assignment to these three variables that can satisfy the formula? If we set x1 equals to 0, x2 equals to 0, and x3 equals to 1, then clearly the formula is not satisfied because the first clause will not be satisfied. And as this formula has ands of clauses, the entire formula will be unsatisfied. But by changing the value of x3 to 0, we can easily see that all the clauses will have satisfying assignment, and hence the whole formula will be satisfied. Now, when the formula is in this conjunctive normal form, that is, the clauses are connected by and the variables inside the clauses are connected by or, and furthermore, when the clause length is arbitrary, then we call this as the CNF-SAT problem. Now, what do we know about the CNF-SAT problem? We know that it's an NP-complete problem. So a polynomial time algorithm, a polynomial time classical algorithm for CNF-SAT problem is highly unlikely. We know that when the clauses are arbitrarily long, the best known classical algorithm runs in 2 power n time. And for the purpose of this talk, I'm going to ignore any polylogarithmic or polynomial factor speedups for CNF-SAT problem. Now, the best known lower bound for CNF-SAT is just linear. So there's a huge gap between the best known classical upper bound and the best known classical lower bound. So consequently, in 2001, Impagliazzo, Zane, and Paturi conjectured that there might not be any faster than 2 power n classical algorithm that solves CNF-SAT. And they called it as the strong exponential time hypothesis, abbreviated to SETH. Now, note that the SETH hypothesis is a much stronger assumption as compared to P not equal to NP. Because when we assume P is not equal to NP, that just indicates super polynomial lower bounds for CNF-SAT problem. But SETH indicates that CNF-SAT requires 2 power n classical amount of time. Okay. But SETH became instrumental in proving various lower bounds. For example, SETH implies specific exponential time lower bounds for many problems in complexity class NP. Interestingly, SETH also implies strong exponential time lower bounds for problems outside NP. For example, conditioned on SETH, it was shown that strong simulation of various quantum computational models take exponential time classically. And surprisingly, SETH also implies many polynomial time lower bounds for problems in complexity class B. For example, a SETH, as a corollary to this, a SETH-based n-square lower bound for proof of useful work scheme was given by Ball, Rosen, Sabin, and Vasudevan. And for the purpose of this talk, we are going to look at these implications of SETH, the polynomial time lower bounds. The first example of such a SETH-based polynomial time lower bound was given by Ryan Williams in 2005. He gave an elegant reduction from CNF-SAT to orthogonal vectors problem, and he showed that any subquadratic algorithm for orthogonal vectors would imply a faster than 2 power n algorithm for CNF-SAT, which would then render SETH false, hence proving a conditional n-square lower bound for orthogonal vectors problem. Now, orthogonal vectors became a central problem for proving lower bounds for many other string comparison problems. So, Bakers and Dyke, Brinkman, Kuhlmann, about the same time, they showed that if there was a subquadratic algorithm for string comparison problems, like the examples that I mentioned, that would imply a subquadratic algorithm for orthogonal vectors problem, which would then imply a faster than 2 power n algorithm for CNF SAT, and hence making SET false. So hence giving lower bounds of hence giving and showing quadratic lower bounds for string comparison problems based on SET. Now, an interesting fact is that all these lower bounds was actually tight. And we can see that SET gives an explanation about why we are not able to find better than n-square algorithm for orthogonal vectors or better than n-square algorithms for edit distance, fresh edit distance, or LCS, these string comparison problems. Okay. But SET doesn't hold true in the quantum setting, because we could use this Grover search algorithm and over all these 2 power n assignments and check if any of these assignments satisfies the formula. And that would take us 2 power n by 2 time. Okay. Therefore, all these set-based lower bounds that we talked about, they don't directly hold in the quantum setting anymore, because the set assumption itself is wrong in quantum setting. Now, both the best classical and the best quantum algorithm for CNF SAT indicates that maybe the description of the formula does barely helps these algorithms. And the quantum speed up that we see is the speed up which comes from this the unstructured search over all these 2 power n assignments. So it is natural to conjecture that maybe there is no faster than 2 power n by 2 quantum algorithm for solving CNF SAT on n variables. And we call this as the basic QSETH conjecture. While we were conjecturing this as a basic QSETH, Aronson et al. Group about the same time also gave this conjecture as the QSETH conjecture. Now let's see how useful this basic QSETH is. Okay. Let's revisit this overview. So because of this basic QSETH, now what we have is that SET requires 2 power n by 2 quantum time. Okay. Now using the same, using this classical reduction from CNF SAT to orthogonal vectors, by just modifying it slightly to make it quantum, we are able to give a linear lower bound for orthogonal vectors problem. And using the similar tricks, we were able to give a linear lower bound for these string comparison problems as well. Okay. Now, while it was interesting, while the linear lower bound was interesting for orthogonal vectors, it wasn't very interesting for the string comparison problems. That's because of two reasons. One, you could get these linear lower bound for string comparison problems unconditionally as well by reducing majority or parity to edit distance or LCS. Okay. And the second reason why it's uninteresting is the best known quantum algorithm for these string comparison problems takes runs in order n square time, quantum time. But the lower bound that we get from the basic QSETH for these problems is still linear. So there's this gap that the basic QSETH is not able to explain. Yeah. So we give a workaround, and that motivates us to give the QSETH framework. Okay. Let's revisit the CNF SAT problem. Now, what was the CNF SAT problem? We are given a CNF formula with n input variables. we would like to know if there's an assignment that satisfies this formula. In other words, what we would like to know is if there is a 1 in the truth table of this formula. Now, what is a truth table? A truth table for a formula on n input variable is a string of 2 power n length, and it is nothing but the concatenation of the formula evaluated on all of these assignments. Okay, so CNF SAT of phi is nothing but the OR property on the truth table of this formula. Okay. Now, the best known quantum algorithm for CNF SAT takes order 2 power n by 2 quantum time. Now, note that the quantum query complexity of OR on strings of length 2 power n is also 2 power n by 2. Now, what if we are not interested in the OR property of the truth table, but we are interested in some other property of the satisfying assignments? Like, say, for example, parity. So we are given a formula phi with n input variables, and we would like to know if there are odd number of satisfying assignments to this phi. So we define that as parity CNF SAT, which is just computing parity on its truth table. Now, how much time will it take to solve parity CNF SAT quantumly? Now, note that the query complexity of parity on this 2 power n bit strings is actually order 2 power n. Right? And it appears as if the CNF SAT, the parity CNF SAT is not amenable to any Grover-like speedups. So it is natural to conjecture that there might not be any faster than 2 power n quantum algorithm for solving parity CNF SAT on n variables. And there are classical analogs to this. They are also called parity SETH. Now, what it appears like is this QSETH conjectures indicate that the time complexity to compute CNF SAT or parity CNF SAT is lower bounded by the query complexity of those corresponding properties on the truth tables of these formulas. But actually, they indicate something stronger, and we'll soon see why. Now, remember the set of CNF formulas that make CNF SAT problem an interesting problem are CNF formulas which are of polynomial length, like poly in n. Okay. So the corresponding set of truth tables for these formulas are going to be only 2 power poly n, which is they're going to be only of size 2 power poly n, which is a tiny fraction of set of all the 2 power n length strings. Okay. Now, the query complexity of this OR property on all these 2 power n bit strings is 2 power n by 2. And fortunately, the query complexity of this OR property on only the small set, that is the set of truth tables of small CNF formulas, is also order 2 power n by 2. That is because the hard instances for OR, the adversarial set of OR, can be generated by from the small CNF formulas. Okay? But that is not the case with the parity property. So the query complexity of parity on all the 2 power n bit string is order 2 power n. But the query complexity of parity on this small set of truth tables is actually, order 2 bar n by 2. In fact, this holds for any property. But while this, this was shown by um, the this efficient query algorithm was first given by Ambainis and Ambainis et al. And it was later improved by Kothari. But an important thing to note here is that this algorithm is very efficient when we look at the number of queries it takes, but it is highly time inefficient. And that motivates us to introduce compression oblivious properties. So what are compression oblivious properties? We say a property P is compression oblivious if the time taken to compute this property on the set of truth tables of small formulas is lower bounded by the query complexity of this property on all strings. Okay. So it's then easy to see that OR is compression oblivious, and it is OR is provably compression oblivious. Okay, as we saw earlier. And parity QSETH, like if we believe that the parity QSETH that I defined earlier is true, then that would imply that our parity property is compression oblivious. Okay. So it is for us reasonable to believe that parity is a compression oblivious property. And we gave a general QSETH conjecture saying that given a Boolean formula or given a formula phi, for all compression oblivious properties P, the quantum time taken to compute this property in the truth table of the formula is at least the query complexity of this property on all strings, all 2 bar n bit strings. And this general QSETH of ours would imply our basic QSETH that we defined earlier. That is because OR is provably compression oblivious, and we are saying that we are saying this conjectures hold for all compression oblivious properties. But for us, our QSETH conjecture, along with the assumption that parity is compression oblivious, would imply parity QSETH. Okay? Now, as our first application of QSETH, what we gave was n power a non-trivial n power 1.5 quantum time lower bound for the edit distance problem. We also give this for the longest common subsequence problem, but the proof idea is very, very similar to the edit distance proof. So let's recall the edit distance problem once. So we are given two strings, A and B, defined over an alphabet set sigma. And edit distance is defined as the minimum number of operations required to convert a string A into string B. And the operations that we allow are insertions, deletions, and substitutions. So let's look at an example. Let's say we have this example where string A is beagle and string B is patches, and we would like to convert beagle to patches with the minimum number of operations. So one way to do it is we delete E and we insert D, we delete L and we insert S, and the edit distance between these two strings is 4. Now, the way we prove this result is we study this classical reduction from satisfiability problem to edit distance problem by Amir Aboud et al. And we notice that by slightly modifying this reduction, the reduction encodes a property, which we name it as p-edit, which is much more complicated than OR. And because this p-edit property is a little complicated and tailor-made property, I'm going to discuss another property, OR of majority, which looks very similar to P edit, but that's not what the reduction encodes. Okay. So let's look at this OR of majority property. Now, imagine you're given a n bit long string, capital N bit long string, and so given this n bit long string, uh, we divide this into root and blocks of root n bits, okay, each. And what we would like to know if there exists a block with majority of ones in it, okay. And the query complexity for this property, the quantum query complexity for this property is proved to be n power 0.75. And using the quantum adversary method, the basic quantum adversary method, we are actually able to show that query complexity of the p-edit property is also n power 0.07, n power 0.75. And assuming this p-edit is compression oblivious and assuming our QSETH conjecture, we are able to prove that given any Boolean formula phi, the time taken to compute p-edit on the truth table of that formula quantumly is at least 2 power 0.75 n. And because of the reduction from satisfiability to the edit distance problem, this translates to a quantum time lower bound of n power 1.5 for the edit distance problem. Now, we have assumed that p-edit is compression oblivious, okay? That is because it's not very easy to prove that a property is compression oblivious. In fact, for many properties which are more complicated than OR, we are able to show that proving compression obliviousness of those properties would actually separate P from P space. That's how hard it is to prove, okay? So that's why we believe it is natural to conjecture that these properties are compression oblivious. And furthermore, by assuming parity is compression oblivious, we were able to show that the n squared classical lower bound given for proofs of useful work by Ball, Rosen, Sabin, and Vasudevan works in the quantum setting as well. And to conclude, we believe that the QSETH framework has numerous applications. For example, we could use our QSETH framework to prove conditional lower bounds for many other problems in BQP. And the low-hanging fruits would be the other string comparison problems. Additionally, we believe that the notion of compression obliviousness of the properties are potentially interesting as well. For example, we would like to know the implication of parity being not compression oblivious. We would like to know what complexity theoretical assumptions it would break if we assume that parity is not compression oblivious. And one other future direction is to study the other key problems that are popular in classical fine-grained complexity, like three-sum and APSP, and to see if those reductions can be applies in the quantum setting as well. And so there's an excellent survey article by Virginia Williams on these fine-grained complexity results. I would now thank you for the attention, and this is the end of the talk.